Welcome to Selvi's Maths Capsule. Here we are going to discuss about algebraic and finite extension. What do you mean by finitely generated extension? An extension K over F is said to be finitely generated if there are elements alpha 1, alpha 2, alpha n in K such that K is equal to f of alpha 1, alpha 2, alpha n. How does the elements of the field f of alpha 1, alpha 2, alpha n looks like? The following lemma says that if K over F is a field extension and alpha and beta are elements of K, then the fields f of alpha beta and the field f of alpha of beta are same. Let us see the proof of this. Note that the field f of alpha beta contains the field f and the element alpha. Therefore, the field f of alpha beta contains f of alpha. Also note that f of alpha beta contains the element beta. Therefore, f of alpha beta contains the field f of alpha and beta. But we know that f of alpha of beta is the smallest field containing both f of alpha and beta. Therefore, f of alpha of beta contained in the field f of alpha beta. For the reverse inclusion, note that the field f of alpha of beta contains f and the elements alpha and beta. But f of alpha beta is the smallest field containing f and the elements alpha beta. Therefore, the field f of alpha beta contained in the field f of alpha of beta. Thus we have the two fields f of alpha beta and f of alpha beta of beta are same. That means the elements of f of alpha beta can be treated as a polynomial in beta with the coefficients in f of alpha. Now, the following lemma says the characterization of a finite extension. The lemma says that the extension K over F is finite if and only if K is generated by a finite number of algebraic elements over F. That means that any finite extension is a finitely generated algebraic extension. Let us see the proof of this. Suppose K over F is a finite extension of degree n. That means that K is a vector space over F and its dimension is n. So let the basis of K as a vector space over F be alpha 1, alpha 2, alpha n. Then for each I, we can consider the extension F contained in f of alpha I contained in K. Then by the formula of degree of extension of tower of extension, we have n is equal to the degree of the extension K over F, and which is same as the degree of the extension K over f of alpha I into the degree of the extension f of alpha I over f. This means that the degree of the extension f of alpha I over f divides n. That means that the degree of the extension f of alpha I over f is finite. That means that the field extension f of alpha I over f is a finite extension. But we know that any finite extension is an algebraic extension. Therefore, f of alpha I over f is an algebraic extension. So that in particular, we get alpha I is algebraic over f. That means that the elements alpha 1, alpha 2, alpha n, the basis of K, are algebraic over f. But K is generated over f by alpha 1, alpha 2, alpha n. Therefore, K has to be equal to f of alpha 1, alpha n. And that means K is generated by a finite number of algebraic elements over f. Now conversely, suppose K is finitely generated by algebraic elements. That means K is equal to f of alpha 1, alpha 2, alpha n, where alpha i's are algebraic over f. Then we can write K is equal to f of alpha 1, alpha 2, alpha n minus 1 of alpha n, and so on. So if we begin with f naught is equal to f and fi is equal to f of alpha 1 alpha I, that means f1 is equal to f of alpha 1, f2 is equal to f of alpha 1 alpha 2, and so on. and Fn is equal to f of alpha 1 alpha 2 alpha n, which is equal to k. So we get, using this notation, we get a tower of field extension, namely f is equal to f naught contained in f1, contained in f2, and so on, contained in fn, which is equal to k. Therefore, by the formula for the degree of extension of that degree of the tower of extension, we have degree of k over f is equal to degree of the extension k over fn minus 1 into the degree of the extension fn minus 1 over fn minus 2 and so on into the degree of the extension f1 over f naught. But it is given that alpha is our algebraic over f. So therefore each alpha I has a minimal polynomial of some degree. So let that degree be ki. So therefore the extension k over the degree of the extension k over fn minus 1 will be definitely less than or equal to the degree of the minimal polynomial of alpha n, that is, which is equal to kn, and so on. F1, the degree of the extension f1 over f naught. F1 is same as f of alpha 1. Therefore the degree of the extension f1 over f naught, here it is exactly equal to k1 and so on. Therefore this degree of the extension k over f will be less than or equal to k1, k2 and so on kn, and which is finite. That means that k over f is a finite extension. Now how do we find the basis of a finite extension? In the last two sessions we have seen these two theorems. One is, if the degree of a minimal polynomial for alpha is n, then a basis of the simple extension f of alpha as a vector space over f is 1 alpha, alpha square and so on alpha raised to n minus 1. That means the simple extension f of alpha or f has a basis, namely 1 alpha, alpha raised to n minus 1. And the formula for the degree of the tower of extension, we have the degree of the extension L over f is equal to the degree of the extension L over k into the degree of the extension k over f. If we have a field extension, tower of field extension f is contained in k is contained in L. Using these two theorems and the lemma we proved today, we can construct the basis of any finite extension. How do we do this? Suppose k over f is a finite field extension. Then, as we see earlier, k is equal to f of alpha 1 alpha n, where alpha is our algebraic over f and they are belongs to k. So we can create k from f by first adjoining alpha 1 to f to get f of alpha 1, and then adjoining alpha 2 to f of alpha 1, we get f of alpha 1 of alpha 2, which is same as f of alpha 1 alpha 2, and repeating this process until we reach f of alpha 1 alpha 2 alpha n, which is k. The first theorem says that if you have a simple extension f alpha or f, and if the degree of the minimal polynomial alpha is n, we have a basis 1 alpha, alpha raised to n minus 1. Using this theorem, we have a basis of f of alpha 1 over f and f of alpha 1 alpha 2 over f of alpha 1. By the second theorem, we have a basis of f of alpha 1 alpha 2 over f. So continuing in this fashion, we can construct a basis for a k over f. Let us see one example. What is the basis and the degree of the extension q root 2 root 3 over q? Consider the tower of extension q root 2 root 3 over q root 2 over q. So note that the field q root 2 root 3, which is same as q root 2 of root 3. Therefore, the degree of the extension q root 2 root 3 over q root 2, which is same as the degree of the minimal polynomial of root 3 over q root 2. But note that h square minus 3 is a minimal polynomial of root 3 over q. Therefore, the degree of the extension q root 2 root 3 over q root 2 will be definitely less than or equal to 2. And it is equal to 2 if and only if the polynomial h square minus 3 is irreducible over q root 2. Because h square minus 3 has degree 2 and it is reducible only if it has a root in q root 2. And that is possible if and only if root 3 is in q root 2. So, suppose root 3 belongs to q root 2. So then we can write root 3 is equal to a plus b root 2 where a and b are in q. After squaring we get 3 is equal to a square plus 2b square plus 2ab root 2. And if ab is not equal to 0, then you can write root 2 is equal to 3 minus a square plus 2b square the whole upon 2ab, which means that root 2 is a rational number, which is not possible. So if b is equal to 0, then we would have root 3 is equal to a, which is also not possible because a is a rational. Finally, if a is equal to 0, then we get root 3 is equal to b root 2 from here, and multiplying both sides by root 2, we get 2b is equal to root 6. That means that root 6 is a rational number, which is also a contradiction. Therefore, root 3 cannot be belongs to q root 2. That means that the polynomial h square minus 3 is reducible over q root 2. Therefore, the degree of the extension q root 2 root 3 over q root 2 is equal to 2, and it has a basis 1 root 3. Now since h square minus 2 is the minimal polynomial of root 2 over q, we have the degree of the extension q root 2 over q is equal to 2 and as a basis 1 root 2. Therefore, the basis of q root 2 root 3 as a vector space over q is the product of each elements of the two bases 1 root 3 and 1 root 2, which is namely 1 root 2 root 3 and root 6. Therefore, the elements of q root 2 root 3 is look like a plus b root 2 plus c root 3 plus d root 6, where a, b, c, d are in q. And therefore the degree of the extension is 4. And the next question says that the fields q root 2 root 3 is equal to q root 2 plus root 3. Thus both the fields are same. Note that root 2 and root 3 belongs to q root 2 root 3. Therefore their sum is also belongs to q root 2 root 3. But we know that q root 2 plus root 3 is the smallest field containing q and root 2 plus root 3. Therefore, q root 2 plus root 3 must contain then q of root 2 root 3. Note that root 2 plus root 3 belongs to the field q of root 2 plus root 3. Therefore, its inverse is also belongs to this field. But the inverse of root 2 plus root 3 is 1 upon root 2 plus root 3, which is same as after rationalization we get root 2 minus root 3 upon 2 minus 3, which is same as root 3 minus root 2. That means that root 2 plus root 3 and root 3 minus root 2 are in the field q root 2 plus root 3. Therefore, their sum is also belongs to q root 2 plus root 3. That means 2 root 3 belongs to q root 2 plus root 3. That means that root 3 belongs to q root 2 plus root 3. Which means that root 2 is equal to root 2 plus root 3 minus root 3 also belongs to q of root 2 plus root 3. Therefore, the field q root 2 plus root 3 contains the field q and the elements root 2 and root 3. But q root 2 root 3 is the smallest field containing the field q and the elements root 2 and root 3. Therefore, q root 2 root 3 is contained in q root 2 plus root 3. So therefore, we have the equality, that is q root 2 root 3 is same as q root 2 plus root 3. Now, what are the properties of algebraic elements? The next lemma says the properties. Suppose K or F is an extension. If alpha and beta is in K are algebraic over F, then their sum, their product, and alpha beta inverse also algebraic over F. Let us see the proof of this. Suppose alpha and beta are algebraic over F of degree m and n. That means that the degree of the minimal polynomial of alpha over f is m, and the degree of the minimal polynomial of beta over f is n. But the minimal polynomial p1h of beta over f of alpha must divide the minimal polynomial p2h of beta over f. By assumption, the degree of p2h is n, and therefore the degree of the polynomial p1 of h is less than or equal to n. Therefore, the degree of the extension f of alpha beta over f alpha, which is same as degree of the polynomial p1 of h, which is less than or equal to degree of p2 of h, which is equal to n. So therefore, by the formula for the degree of the tower of extension, we have f of alpha, the degree of the extension f of alpha beta over f is same as the degree of the extension f of alpha beta over f alpha into the degree of the extension f alpha over f, and which is less than or equal to n times n. That means that the degree of the extension f alpha or f alpha beta over f is a finite extension, but every finite extension is algebraic, therefore this extension is algebraic. In particular, every element of the field f of alpha beta is algebraic over f. Therefore, since alpha and beta belongs to the field f of alpha beta, we get alpha plus or minus beta, alpha beta inverse are algebraic over f. So what does this mean? This means that the collection of algebraic elements forms a subfield. So precisely, let L be an arbitrary extension of f. You take the collection of elements of L that are algebraic over f. That collection we call it as K. Then K is a subfield of L. This follows from the previous lemma. We now see another property of algebraic extension. The next lemma says that if L over K is algebraic and K over F is also algebraic, then L over F is algebraic. To prove this, let us consider an element alpha in L. Since L over K is algebraic, alpha satisfies some polynomial fx, which is equal to a0 plus a1h plus an h raised to n in kx. So that means a0, a1, a2, an r belongs to K. Let us consider the field f of alpha a0, a1, a2, an, which is generated over f by alpha and the coefficients of this polynomial. So we can treat fx as a polynomial over f of alpha a0, a1, an. Since K over F is algebraic, the elements a0, a1, an which belongs to K are algebraic over F. Therefore, the extension f of a0, a1, an over f is finite, because we have seen that a finitely generated algebraic extension is a finite extension. So since the minimal polynomial of alpha over f of a0, a1, an is a divisor of f of x, therefore the degree of the extension f of alpha a0, an over f of a0, a1, an is less than or equal to n. Therefore, using the formula for the degree of the tower of extension, we have the degree of the extension f of alpha a0, an over f, which is same as f of degree of the extension f of alpha a0, an over f of a0, an into the degree of the extension f of a0, an over f. So, because the right hand side both the extensions are finite, we get the extension f of alpha a0, an over f is finite. Which implies, but we know that any finite extension is an algebraic extension. This means that the extension f of alpha a0, an over f is an algebraic extension. In particular, alpha is algebraic over f. This is true for any element alpha over n. Therefore, we get L over f is an algebraic extension. In the next session, we discuss about the composite field. Thank you for learning with Selby's Maths Capsule. Thank you.